Okay, tan 210, we're going to do another 211, sorry. We're going to go ahead and do another frames problem here. So here in this one, we're asked to find the reactions at E and the force in member BC. Okay, so I want you to take a second, think about it. Don't just watch the video. Go ahead and pause while you think about what approach you're going to take to solve this, and then come back and use the video to troubleshoot. Okay. All right, so what did you do? So in this case, we know we're going to need to separate some things, right? We need to know what those reaction forces at E are, and we need to know what's happening inside member BC. So I would say we should probably separate member EC and recognize, right? Find your two force members. Those give you some lines of actions of forces and eliminate unknowns. Draw the free body diagrams and apply the equations of equilibrium. So let's start with the one that might get us everything and then see how far that gets us. So if we need to know the reactions at E and what's happening in member BC, we could do a free body diagram of member EC and see what that gives us. So we'll set up a standard coordinate system. I'll just draw a line here that represents our member EC, and then let's apply the loads. So at E, we've got a pin joint, so we know we're going to have reactions EY and EX. Force at member AD, where it's connected at point D. So we've got a point D here. Recognize that member AD is a two-force member, so we know the line of action of this one. So this is the force, I called it dA here. And then at point C, we have two things happening. Right, I'm going to scooch this label over. We have the external force being applied, the 5 kilonewtons down. And then we have whatever is happening due to member BC, which is also a two-force member, or CB. It doesn't matter, either way. All right, so we definitely have too many unknowns to be able to solve this with the equations of equilibrium. So let's see if we can get rid of some of them. What's another way? We could take a look at the free body diagram of the whole thing, right? And see if we can get through this. So let's draw a free body diagram of the whole structure. So here we have the top half, we have the side, here, and then we have A coming down roughly into the middle, right? Now what's happening here? Our external loads, coming a little bit more, so we've got this triangular load. And then at A, we're pin connected, so we're going to have AX and an AY. 5 kilonewtons external again, and then again the reactions at E, EX, and EY. So what do? Probably first thing we should do is figure out what's happening with these forces. So what we can recognize, right, this is known, 4 kilonewtons per meter is the peak of that distributed load, and it goes down to 0 on either side at A and B. Now, if you can see, we could take the moments at A, right, here. Everything else is known except for EX and EY, and we could get EX straight away, right? So what if we use that approach to try and solve for this? So what do we need to do with the 4 kilonewtons? How do we handle that distributed load? So there's a couple ways we can handle this. So let's redraw what this is equal to. First, you might say, well, there's two triangles, so it's really the same, right? It's equivalent to two forces that are acting on this thing. So we can take this distributed load, and we can take this side and this triangle here and replace it with two sets of forces, right? So this was D is coming down. And we know that it's going to act a third of the way from the bigger side of the triangle. And that these forces are equal to 1/2 times the base. So the base was the 1.5 meters here. Drawing on the left. Times the height, the 4 kilonewtons per meter. And that's also going to be equal to this F here. Now if we do sum of moments with respect to A, what you'll actually find out is that you can still combine these forces and have their equivalent force. This is the same as like a distributed load, right? In the sense that you can have these two forces actually acting at point D. And it'll actually be the exact same thing. As further simplifying this distributed load. So I'm going to draw them here. So these are the same. And now these are the same as well. So we can take these two and say this is exactly the same as 2F. Right? Where F is what we solved for before, and that ends up being 6 kilonewtons. If you don't believe me, you can solve for the sum of moments using this one here. And I promise you, you'll get the exact same answer as using this one here. Okay, so let's work on this. So we're going to take the sum of moments with respect to A, right? Positive counterclockwise. So pause for a second and make sure you can get this calculation done, right? Correctly. So we have what? Coming back, EX times its moment arm 2 meters minus the 6 kilonewtons. So this is really making sure you're good with the right-hand rule here. Minus the 5 kilonewtons from the outside. Its moment arm 3 meters equals 0. And when you solve this, you'll find EX is equal to 12 kilonewtons. Okay, so we've got one. And our directions are correct. So there's one of our answers. Now what do? Can we come back here to our original free body diagram? Now that we know what EX is, what else can we do here to solve for this? Pause for a minute while you think about that. How about solving back to this equation? We can get this free body diagram and start working it through. So now we have 1, 2, 3. We have 3 unknowns now, so we should be good to go. Sorry for all the scrolling up and down. Okay, so we've solved for EX. Oh, what is that going to give us? Right. If we come here, we can do sum of forces in the X direction, right? And you should see that if we know EX, the only other force in the X direction is going to be dA, and that should give us FdA. So you should look at these and think, okay, what am I going to do? Instead of just picking a diagram randomly, think about what you're going to actually solve from it. And if you can't see that, then think carefully about which diagram you're going to use and which equations you're going to need to start solving for. So let's do that. Sum of forces X. We have EX, and now we have this angle here, theta. So what's our triangle? I'm drawing now on the left. I've got this triangle here, right, of 1.5, 2 meters. Again, I plug this into MATLAB. Make sure you can solve for this. What this theta ends up being is equal to 53 degrees. So now we can finish this. EX minus the Fx component of force dA, so that's minus FdA cosine theta equals 0. Can solve for FdA. Should get 20 kilonewtons. Okay? It's just a means to an end. The question doesn't ask for FdA, But now that we have FDA, we can go ahead and solve for EY and FCB. Right? How do we do that? So we can take sum the moments about point C, positive counterclockwise. Right? If we do that, FCB won't be in the equation, EX won't be in the equation, and only the Y component of FDA will be in the equation, but now we know its magnitude, so we're good there. And EY, the only unknown, will be in the equation, so we're good to go. So let's set this up. So EY is going to contribute a negative moment, EY times its moment arm, 3 meters, minus the Y component, FDA sine theta, times its moment arm, 1.5 meters, equals 0. Nothing else is in this moment equation. So when you solve this, you're going to find that EY is actually equal to minus 8 kilonewtons. And that's exactly what you'll put in, right? So it means the arrow is pointing the wrong way. So in magnitude, EY is equal to 8 kilonewtons, but it actually is pointing in the negative direction. So it's going to be a negative 8 if you're asked for the force vector. And now, I'm going to shrink this down. We can take all this and get our last equation. Sum of forces Y, positive. And that's going to get us our FCB, the one that we've been wanting, the last step. So we have EY plus the Y component of FDA sine theta, plus FCB, minus 5 kilonewtons equals 0. So again, simplify this as much as you can before you go to MATLAB. Right? So we can isolate FCB. It's going to be equal to minus EY minus FDA sine theta plus 5 kilonewtons. We just figured out what EY is. So when you break this down, put it in, you find that FCB is equal to minus 3 kilonewtons. And that's the force in member CB. And that's it.